Welcome to For Science Salah Lotfy channel, where science meets curiosity. في هذه القناة لا نكتفي بعرض الأبحاث العلمية، بل نترجمها إلى المعرفة التي تصل إليك أينما كنت. Our mission is to make global scientific research understandable, accessible, and multilingual. جميع الفيديوهات العلمية هنا مترجمة إلى اللغة العربية، بالإضافة إلى لغات عالمية أخرى. French, Spanish, German, Urdu, and more. Because science speaks every language. نعم، العلم يتحدث بكل اللغات، ونحن نحرص أن يصلك بلغتك. If you're passionate about science, you're in the right place. اشترك الآن وابدأ رحلتك مع العلم خطوة بخطوة. For Science Salah Lotfy channel, العلم للجميع.
Welcome to For Science Salah Lotfy channel. Today we will explore an exciting piece of research that combines physics, material science, and advanced electronics. A study on flexible polymer composites that achieve negative permittivity at microwave frequencies. This is not just theory, it is a breakthrough with direct implications for wireless communication, flexible electronics, and wearable devices. The core idea. The research investigates composites made from ethylene vinyl acetate or EVA, reinforced with small amounts of copper particles. What makes this special is that these materials demonstrate Lorentz-type negative permittivity, a property where the dielectric constant becomes negative, while still maintaining flexibility and thermal stability. Negative permittivity is a key feature in the design of metamaterials, which are used for revolutionary technologies such as superlenses, cloaking devices, and advanced antennas. The challenge and the solution. Traditionally, achieving negative permittivity requires a high concentration of metallic fillers, but this creates two major problems. 1. The negative permittivity values become too large, which is undesirable for impedance matching. 1. The mechanical flexibility of the polymer is lost. This study solves that problem. By keeping the copper content below the percolation threshold, the researchers managed to obtain weak, tunable, negative permittivity, just enough for practical applications, while preserving elasticity and heat resistance. How the study was conducted. The team prepared flexible EVA copper composite films with different copper loadings, 0, 10, 20, 30, and 40 weight%. Using multi-layer casting and hot pressing, they created homogeneous films where copper was well distributed. They then used advanced techniques, SEM and EDX to confirm uniform particle distribution, XRD to study crystallinity, TGA and DMA to measure thermal and mechanical stability, and dielectric spectroscopy over a wide frequency range, from 0.1 Hz to 3 GHz. Key findings. The results were impressive. The composites maintained thermal stability up to 340 degrees Celsius, suitable for industrial use. Mechanical testing showed improved glass transition temperature and cross-link density, meaning better flexibility and durability. At lower frequencies, the composites had low dielectric losses, making them suitable for RF applications. Most importantly, at 2 GHz, the 40% copper composite exhibited negative permittivity values of about 12, perfectly modeled by the Lorentz equation. Why this matters? From a scientific perspective, this research advances our understanding of how to fine-tune electromagnetic properties in flexible materials. From a technological perspective, it opens the door to next-generation antennas for wireless communication, microwave filters with narrow passbands, wearable electronics and smart sensors that are both flexible and high-performing. Economically, reducing the amount of copper needed makes production cheaper and more sustainable. Technologically, this aligns with the global race toward flexible, lightweight, and efficient devices. For society, it means better performance in medical wearables, communication systems, and even aerospace applications. And for education, it demonstrates how interdisciplinary research, combining physics, chemistry, and engineering, can lead to real-world innovations. In short, this research by Dr. Emad Mousa and his colleagues from Cairo University and the National Institute of Standards in Egypt provides a valuable step forward in developing practical metamaterials for advanced industries. Stay tuned as we dive deeper into the details of this fascinating study and uncover how such scientific advancements are shaping the future of technology. This is For Science Salah Lotfy channel. Welcome to For Science Salah Lotfy channel. Today, we present to you a recently published scientific contribution that connects advanced physics, polymer science, and electronic materials. Title of the research: Lorentz-type negative permittivity of flexible ethylene vinyl acetate copper composites below the percolation threshold. This work has been published in the International Journal Polymer Bulletin. Received March 19, 2025. Revised July 23, 2025. Accepted July 31, 2025. Copyright. The research is a collaborative effort from Cairo University and the National Institute of Standards in Egypt. The team includes Associate Professor Dr. Emad Mousa, Physics Department, Faculty of Science, Cairo University, Cairo, Egypt. Corresponding author, Research Assistant Ms. Rania Salama, Volume and Fluid Flow Department, National Institute of Standards, Giza, Egypt. Professor Dr. Mohammad Abu-Abdeen, Physics Department, Faculty of Science, Cairo University, Cairo, Egypt. Professor Dr. Gamal Nazar, Physics Department, Faculty of Science, Cairo University, Cairo, Egypt. The focus of the research. This study explores a cutting-edge concept in materials science, the development of flexible polymer composites that exhibit Lorentz-type negative permittivity. The researchers used ethylene vinyl acetate, EVA, combined with copper particles to achieve negative permittivity values at gigahertz frequencies, while maintaining both flexibility and thermal stability of the polymer matrix. Why this is important? Negative permittivity is not a usual property in conventional materials. It is a feature that allows the design of metamaterials, engineered materials that can manipulate electromagnetic waves in extraordinary ways. Such materials open the door for technologies like advanced antennas for wireless communication, microwave filters with narrow frequency bands, wearable electronic devices, electromagnetic shielding, and even cloaking applications. Key achievement. Unlike traditional composites that require a high amount of metal fillers, often compromising flexibility, this work shows that even below the percolation threshold, copper can induce weak negative permittivity. In fact, at around 40 weight% copper, the EVA composites demonstrated negative permittivity of about 12 at 2 GHz, modeled successfully using the Lorentz resonance model. Scientific and technological impact. Scientific value. The research provides a balanced method to achieve tunable electromagnetic properties without losing the inherent advantages of the polymer. Technological value. It supports the advancement of flexible and wearable electronics operating in the radio and microwave frequency ranges. Economic value. By lowering the amount of copper required, the study presents a cost-effective and sustainable pathway for industrial applications. Educational value. It demonstrates how interdisciplinary research, combining physics, materials science, and engineering, can lead to real-world innovation. In summary, this research by Associate Professor Dr. Emad Mousa, Research Assistant Ms. Rania Salama, Professor Dr. Mohammad Abu-Abdeen, and Professor Dr. Gamal Nazar represents an important step in the design of new polymer composites for advanced communication technologies and next-generation electronics. Stay with us on For Science Salah Lotfy channel as we continue to highlight groundbreaking scientific contributions that shape the future of technology and society. Welcome to For Science Salah Lotfy channel. Today we are diving into a fascinating scientific journey at the intersection of physics, materials science, and electronic engineering. Our focus is a study recently published in Polymer Bulletin titled Lorentz-type negative permittivity of flexible ethylene vinyl acetate copper composites below the percolation threshold. This research explores how polymer composites can be engineered to exhibit negative permittivity, a highly unusual and powerful property that opens the door to groundbreaking technologies. The abstract in simple terms. Polymer composites are now central to the development of flexible electronics and wearable devices. Scientists have discovered that if we can tune a property known as permittivity into the negative range, we gain access to unique electromagnetic behaviors. This is especially crucial for designing metamaterials, artificially engineered materials with extraordinary properties. But there's a problem. Traditionally, achieving negative permittivity requires adding a high concentration of metallic fillers, like copper or other conductive materials. While this increases the effect, it also destroys the flexibility of the polymer and makes the material too stiff for practical use. The challenge, therefore, is to find the right balance to achieve useful negative permittivity without sacrificing the elasticity and thermal stability of the host polymer. In this research, the scientists demonstrated that it is indeed possible. Using ethylene vinyl acetate, or EVA, combined with copper, they fabricated composite films that exhibit weak but tunable negative permittivity at microwave frequencies, while still maintaining the flexibility and heat resistance of EVA. Why permittivity matters. Permittivity describes how a material responds to an electric field. Most materials have positive permittivity, which simply means they store and transmit electrical energy in a predictable way. But when permittivity becomes negative, something remarkable happens. They can bend light or electromagnetic waves in the opposite direction. They allow for negative refraction, which makes possible superlenses that break the diffraction limit. They can create effects like the reverse Doppler shift and even cloaking mechanisms that hide objects from detection. Because of these properties, negative permittivity materials are now considered a hotspot in materials science. They are the building blocks of metamaterials, which can manipulate waves in ways nature does not normally allow. From metamaterials to polymer composites. Traditionally, metamaterials were designed using artificial periodic structures, carefully engineered at the micro or nano scale. But researchers discovered that you don't always need perfectly periodic structures. Heterogeneous composites, that is, mixtures of polymers and fillers, can also achieve negative permittivity. Different systems have been explored, including metal-based composites, carbon-based composites, semiconductor and ceramic composites, conductive polymers. Among these, polymer composites have a unique advantage. They are flexible. Previous challenges. Earlier studies showed that when metals like copper are added to polymers, the composite can indeed reach negative permittivity. However, the negative values were often too extreme. For example, one study on polyphenylene sulfide with copper reached values as low as 104 at 100 MHz when copper concentration hit the percolation threshold. Another study using copper/silica-coated fillers still showed negative values around 178 at 1 MHz. While impressive, these values are too large for practical impedance matching. And more importantly, such high filler concentrations, up to 70% of the material, make the polymer brittle and unusable for flexible electronics. Thus, the real question has remained unsolved. Can we design a composite that achieves controlled, weak, negative permittivity without losing flexibility? Thus, the real question has remained unsolved. Can we design a composite that achieves controlled, weak, negative permittivity without losing flexibility? The new approach. This is exactly what the current study set out to address. The researchers chose EVA, ethylene vinyl acetate, a polymer known for excellent flexibility, high thermal stability, up to 300 degrees Celsius, good adhesion, and impact strength. They then incorporated copper particles at different weight percentages, 0, 10, 20, 30, and 40%. Instead of random mixing, they used a multi-layer casting-assisted hot pressing method to achieve homogeneous films where copper particles are evenly distributed. To verify the structure and properties, the team applied a series of advanced techniques, SEM and EDX to study the microstructure and particle distribution, TGA to measure thermal stability, DMA to evaluate mechanical flexibility, and dielectric spectroscopy across a wide frequency range, from 0.1 Hz up to 3 GHz. The results: 1. Flexibility and stability preserved. Even with copper loading up to 40%, the composites retained EVA's elasticity and could withstand high operating temperatures up to 340 degrees Celsius. 2. Low dielectric losses. Across low frequencies, all samples maintained weak frequency dependence and low dielectric losses, an important feature for RF applications. 3. Negative permittivity achieved. Most importantly, the sample with 40% copper by weight, about 6% by volume, exhibited negative permittivity values of 12 at 2 GHz. The dielectric behavior matched the predictions of the Lorentz resonance model, confirming that the negative permittivity here originates from dielectric resonance rather than plasmonic oscillations. Why this matters for technology. Flexible antennas for next-generation communication systems, microwave filters with precisely controlled frequency responses, wearable electronics that are both durable and high-performing, potential use in superlenses, cloaking devices, and EMI shielding. And because the copper content is kept below the percolation threshold, the composites remain cost-effective and easy to manufacture. Broader significance. From a scientific standpoint, this research advances our understanding of how to balance filler content to achieve target electromagnetic properties without losing mechanical performance. From an industrial standpoint, it lays the foundation for new classes of flexible, lightweight, and affordable materials that can be directly integrated into consumer electronics, medical wearables, and even aerospace technologies. Closing in summary, this research shows us that weak negative permittivity can indeed be achieved in flexible polymer composites using low amounts of metal fillers. The outcome is a material that combines advanced electromagnetic properties with flexibility, thermal stability, and durability. It is a step forward in the ongoing quest to design practical metamaterials and flexible electronic devices. Stay with us here at For Science Salah Lotfy channel as we continue to highlight scientific breakthroughs that bring us closer to the technologies of tomorrow. Welcome to For Science Salah Lotfy channel, Materials and Sample Preparation. The process began with the polymer ethylene vinyl acetate, EVA. A 5-gram sample of EVA, containing 12% vinyl acetate, was dissolved in 100 milliliters of toluene at 90 degrees Celsius for 1 hour using a magnetic stirrer. A 5-gram sample of EVA, containing 12% vinyl acetate, was dissolved in 100 milliliters of toluene at 90 degrees Celsius for 1 hour using a magnetic stirrer. A 5-gram sample of EVA containing 12% vinyl acetate was dissolved in 100 milliliters of toluene at 90 degrees Celsius for 1 hour using a magnetic stirrer. After this, copper powder was gradually added to the dissolved EVA solution with continuous stirring for another 30 minutes. To explore the effect of different metal loadings, the researchers prepared composites with 0, 10, 20, 30, and 40 weight% of copper relative to EVA. To improve the uniformity between the polymer and the filler, a multi-layer hot press method was employed. The EVA copper solution was divided into 4 equal parts, and each portion was cast into a thin film on glass petri dishes. These films were dried at 70 degrees Celsius in a vacuum oven for 2 hours. These films were dried at 70 degrees Celsius in a vacuum oven for 2 hours. The dried films were then carefully stacked in a sandwich-like arrangement, layer over layer, before being placed inside a stainless steel mold with dimensions of 50 x 50 x 3 millimeters. The dried films were then carefully stacked in a sandwich-like arrangement, layer over layer, before being placed inside a stainless steel mold with dimensions of 50 x 50 x 3 millimeters. Finally, the stack was hot-pressed at 200 degrees Celsius under 5 megapascals pressure to produce uniform composite sheets. This preparation ensured not only the incorporation of copper particles into EVA, but also maintained the flexibility of the resulting films. The characterization techniques. To evaluate the prepared samples, a series of advanced analytical techniques were applied. 1. Scanning electron microscopy, SEM. A Quanta 250 field emission gun SEM was used, equipped with energy dispersive X-ray spectroscopy, EDX. Cross-sectional images were taken after freeze-drying and fracturing the films with liquid nitrogen, ensuring detailed observation of the copper distribution inside the polymer. 2. X-ray diffraction, XRD, conducted with an expert pro diffractometer using Kuka radiation across a range of 10 degrees to 90 degrees. This helped determine the crystallinity of both EVA and copper phases within the composite. 3. Thermogravimetric analysis, TGA, performed under nitrogen gas using a Mettler-Toledo system, from room temperature up to 700 degrees Celsius at a heating rate of 10 degrees Celsius per minute. 4. Dynamic mechanical analysis, DMA, conducted with a Triton Instruments Analyzer in tension mode at 1 Hz frequency. The temperature range spanned from 100 degrees Celsius to plus 100 degrees C, providing insights into the glass transition behavior and mechanical flexibility. For the dielectric analysis, specimens were cut into disc-shaped pieces, 10 mm in diameter and 3 mm thick, and coated with a thin gold layer to enhance conductivity. 2 frequency regions were explored, from 0.1 Hz to 10 MHz, using a broadband dielectric spectrometer. Here, samples were mounted between 2 gold-plated electrodes in a sandwich capacitor configuration, from 0.1 Hz to 10 MHz, using a broadband dielectric spectrometer. Here, samples were mounted between 2 gold-plated electrodes in a sandwich capacitor configuration, from 20 MHz to 3 GHz, using an impedance analyzer by Keysight Technologies. The sample was placed between gold electrodes, shielded in a copper cell, and connected through an APC7 connector.
Welcome back to For Science Salah Lotfy channel. In this part of our episode, we turn to the results and discussion section of the study on Lorentz-type negative permittivity of flexible EVA copper composites. Here, we will carefully review how the prepared composites were analyzed and what the data revealed about their structure, crystallinity, and thermal stability. Let's begin with the scanning electron microscopy, SEM, images of the EVA composite containing 40 weight% copper. At both low and high magnifications, 60,000x and 120,000x, the micrographs revealed a dense and homogeneous structure. Importantly, there was no evidence of layer separation or particle agglomeration. This is crucial. In many polymer metal composites, filler particles tend to cluster together, leading to poor mechanical and electrical performance. But here, the SEM and EDX elemental mapping confirmed that copper particles were uniformly dispersed throughout the EVA matrix. This uniformity is one of the key reasons why the composites were able to achieve controlled negative permittivity while still maintaining flexibility. Next, the team investigated the crystal structure using X-ray diffraction, XRD. The diffractograms compared pure copper metal, pure EVA polymer, and EVA composites with different copper loadings. For copper, characteristic crystalline peaks appeared at 43.39 degrees, 50.68 degrees, and 74.41 degrees, corresponding to the 111, 200, and 220 crystal planes. For EVA, two sharp crystalline peaks were observed. A strong 110 reflection at 21.58 degrees, and a weaker 200 peak at 23.86 degrees, superimposed on a broad hump caused by the disordered vinyl acetate-rich regions. When copper was incorporated, both sets of peaks were clearly visible. As copper content increased, the intensity of copper peaks rose, while EVA peaks diminished. This indicates that the two phases remained structurally distinct, forming a biphasic system. In other words, the copper particles did not chemically interact with the polymer matrix. To quantify this, the researchers calculated the crystallinity index, CI%, of the EVA phase. Now let's examine thermal stability, tested by thermogravimetric analysis. Pure EVA undergoes two major decomposition stages. 1. The first, from about 349-400 degrees Celsius, corresponds to the release of acetic acid. 2. The second, from about 446-490 degrees Celsius, is linked to the breakdown of unsaturated polymer chains, releasing gases like ethylene, methane, and carbon dioxide. At 600 degrees Celsius, pure EVA left behind only 1.3% residue. When copper was added, the decomposition behavior was broadly similar, but with some important differences. The onset of degradation shifted slightly, with the 40% Q sample beginning at around 340 degrees Celsius, only 9 degrees Celsius lower than pure EVA. This shows that even at high loading, EVA retained much of its thermal stability. The char residue at 600 degrees Celsius increased dramatically with copper content, rising to 42% for the 40% Q-loaded sample. This is expected since copper does not decompose, but instead stabilizes the polymer matrix. Interestingly, samples with 10% and 20% copper showed slightly higher decomposition temperatures in the second stage compared to pure EVA, indicating a stabilizing effect at moderate loading levels. This balance between thermal resistance and filler content is critical for real-world applications, ensuring that composites can operate safely in high-temperature environments, such as in electronic circuits or communication devices. So what do these findings tell us? 1. SEM and EDX proved that copper was evenly distributed without agglomeration. 2. XRD analysis showed how copper particles influence crystallinity, initially enhancing order at low loadings, but reducing it at higher concentrations. 3. TGA analysis confirmed that EVA retains its essential thermal stability even at high copper loadings, with only minor shifts in degradation temperatures. Together, these results establish EVA composites as structurally sound, thermally stable, and uniformly dispersed materials, setting the stage for the next step, exploring their dielectric and electromagnetic properties, where negative permittivity comes into play. The detailed characterization confirms that it is possible to engineer flexible, thermally stable composites that integrate metallic fillers without sacrificing structural integrity. In our next part, we will move into the most exciting section, the dielectric properties and electromagnetic response, where these composites reveal their ability to achieve weak negative permittivity at gigahertz frequencies, paving the way for future metamaterials and flexible electronic applications. Stay tuned with us here at For Science Salah Lotfy channel as we continue this journey into cutting-edge materials research.
Welcome to For Science Salah Lotfy channel. Today we continue our journey into the fascinating research on EVA polymer composites, a study that merges materials, science, electronics, and the future of advanced communication systems. Thermogravimetric analysis, TGA. Let us begin with the thermal stability of these composites. The researchers compared pure EVA with EVA-Q composites across different copper loadings. Pure EVA showed two main decomposition stages. The first stage, around 349–400 degrees Celsius, corresponds to the release of acetic acid. The second stage, between 446–490 degrees Celsius, reflects the breakdown of polymer chains. But when copper particles were introduced, something remarkable happened. The decomposition temperatures shifted slightly, with 10% and 20% copper-loaded samples showing higher stability in the second stage. This indicates that the presence of copper particles alters how the polymer decomposes. Even more striking was the residual weight left at 600 degrees Celsius. Dynamic mechanical analysis, DMA. To understand how these composites perform under real-world conditions, the study probed their mechanical behavior across a range of temperatures using a powerful technique, dynamic mechanical analysis, or DMA. DMA applies a small oscillating force to a sample while its temperature is ramped. The machine measures the material's response, separating it into two components: the storage modulus, representing its stiffness, and the loss modulus, representing its ability to dissipate energy as heat. First, the pure EVA polymer provided a baseline. Below -50 degrees Celsius, it's in the glassy region. Here, polymer chains are frozen and locked into a rigid state. With little mobility, the material is stiff and brittle, much like hard plastic. As the temperature rises into the glass transition region, between -50 and 40 degrees Celsius, the chains gain enough energy to begin moving. This is a critical phase where the material transforms from a rigid solid to a soft, rubbery substance, exhibiting both elastic and viscous properties, a state known as viscoelasticity. Finally, above 40 degrees Celsius, the material enters the rubbery region. The polymer chains have significant freedom of movement, allowing the material to stretch and deform easily. The stiffness drops and then levels off into a rubbery plateau, a key indicator of the polymer's internal network structure. So, what happens when copper particles are introduced? The storage modulus data shows an immediate and significant increase in stiffness. The rigid copper particles act as a reinforcement, restricting polymer chain movement and making the composite much harder. This effect grows stronger with higher copper content. The loss modulus, measuring energy dissipation, tells a more complex story. At lower concentrations, copper particles increase energy dissipation, likely due to friction between the polymer chains and filler surfaces. But above 30% copper, the particles become so densely packed they form their own rigid network. This severely restricts chain mobility, reducing internal friction and therefore energy dissipation. The data from the rubbery plateau offers another crucial insight. From this, the team calculated the cross-linking density, a value quantifying how interconnected the polymer chains are. The results showed that as more copper was added, the cross-linking density increased. This is a significant finding. It suggests the copper particles aren't just passive fillers. They actively promote a more tightly bound network, acting as junction points that encourage chains to pack more efficiently. This creates a composite that is not only stiffer, but also more dimensionally stable and robust. With our composites prepared, we turned to characterizing their electrical behavior, focusing on their dielectric properties. This defines how a material responds to an electric field, a critical factor for electronics. Our analysis began in the low-frequency range, from 0.1 Hz to 10 MHz. Using impedance spectroscopy, we found the dielectric constant, a measure of energy storage, was relatively stable. A slight drop-off with increasing frequency pointed to interfacial polarization. This effect, also known as the Maxwell-Wagner-Sillars effect, occurs at the microscopic boundary between the insulating EVA polymer and the conductive copper particles. Charge carriers accumulate at these interfaces, creating countless tiny dipoles that enhance the material's energy storage. Crucially, as copper content increased, the dielectric constant rose predictably. The dispersed copper particles, separated by the insulating polymer, form a vast network of microcapacitors. Each particle acts as a capacitor plate, with the EVA polymer as the insulator. Adding more copper is like adding more capacitors to the circuit, boosting the material's overall energy storage. This provides a direct method for tuning the dielectric constant by simply adjusting the filler concentration. We also measured the dielectric loss, which quantifies energy dissipated as heat. This loss factor also increased with higher copper content, reflecting greater conduction losses. As copper particles get closer, a small amount of charge can leak through the polymer. While this loss increased, it remained at acceptably low levels for many applications. This led us to examine the material's bulk conductivity to see if we had crossed the percolation threshold, the point where filler particles form a continuous conductive path. Remarkably, even at a high loading of 40% copper, the material remained insulating. This confirmed our synthesis method achieved excellent particle dispersion, preventing the formation of a conductive network. This gives us a material with a high dielectric constant that is not conductive. This combination of a stable, high, and tunable dielectric constant, coupled with controlled conductivity, makes these composites highly promising for radio frequency applications. Next, we pushed our investigation into the high-frequency range, from 20 MHz to 3 GHz. This is the operational spectrum for modern wireless technologies, where a material's behavior can be vastly different. What we discovered was a new and powerful characteristic. In this higher range, all samples displayed a distinct dielectric resonance, a specific frequency at which energy absorption peaks. The most significant finding was that this resonance frequency was not fixed. It systematically shifted to lower frequencies as the copper content increased. The microcapacitor network within the composite has its own natural resonance, and by adding more copper, we were effectively retuning the system. This tunability allows for the design of smart materials tailored to interact with specific electromagnetic frequencies, opening doors for advanced antennas and frequency-selective devices. The discovery of negative permittivity in the simple composite is perhaps the most profound outcome of this research. To understand why, we first need to grasp what permittivity is. In simple terms, it's a measure of how a material stores electrical energy when exposed to an electric field. Nearly every material found in nature, from water to wood to plastic, has a positive permittivity. Negative permittivity, however, is a characteristic of so-called metamaterials. These are not materials found in nature, but rather they are artificially engineered structures designed to exhibit extraordinary properties. By achieving negative permittivity, a material can manipulate electromagnetic waves, like radio signals or light, in ways that are physically impossible for natural materials. This opens the door to futuristic applications, from superlenses that can see beyond the diffraction limit to, in theory, cloaking technologies. What makes this discovery so significant is that the team achieved this metamaterial-like property not with complex, expensive nanofabrication, but with a straightforward, scalable mixture of a common polymer and copper particles. The fact that the resonance behavior was successfully modeled using the classical Lorentz model adds a powerful layer of validation. This confirms that the observed negative permittivity isn't a measurement error or a random anomaly. Instead, it is a predictable, repeatable phenomenon rooted in the fundamental physics of how the composite structure interacts with electromagnetic fields. This robust confirmation provides a solid foundation for designing future devices. Scientific and technological implications. First, let's consider thermal performance. The study showed the composite's thermal stability dramatically increased, withstanding temperatures over 300 degrees Celsius. This is a massive leap from the 160-degree limit of pure EVA. This enhancement makes the material exceptionally well-suited for electronics operating in demanding environments. Imagine sensors placed within a hot car engine bay, durable components for aerospace applications, or power electronics in compact devices where managing heat is a critical design bottleneck. This material doesn't just survive the heat, it thrives in it. Second, its mechanical behavior. The enhanced cross-linking within the polymer matrix does more than just add thermal resistance. It significantly improves the material's durability while preserving its inherent flexibility. This combination is the holy grail for the next generation of electronics. Think of smart textiles that integrate sensors directly into the fabric, biomedical implants that must flex with the body without failing, or truly foldable smartphones. The robust structure also ensures the copper particles remain locked in place, guaranteeing stable electrical performance even after thousands of cycles of bending and stretching. Third, the material's versatile electrical properties. One of the most powerful features of this composite is its tunability. By precisely controlling the concentration of copper particles, engineers can dial in the exact conductivity and dielectric behavior needed for a specific task. This transforms it from a single material into a versatile platform. It can be engineered to create highly efficient patch antennas for 5G and future 6G communication, or it can be formulated to act as a powerful shield, absorbing and blocking electromagnetic interference that could otherwise disrupt sensitive electronic components. And finally, this brings us back to the discovery of negative permittivity. This property, observed around the 2 GHz frequency, is a gateway to miniaturization and enhanced performance. Materials with negative permittivity can be used to build antennas and microwave filters that are significantly smaller than conventional designs operating at the same frequency. This is critical for packing more power and functionality into ever-shrinking devices like IoT sensors, advanced drones, and portable communication systems. It paves the way for a new generation of compact, efficient, and powerful wireless technologies. Conclusion. In conclusion, this study is a remarkable demonstration of material science innovation. It shows how a humble and widely available polymer, EVA, can be elevated into a high-performance, multifunctional composite through a simple, scalable process. By methodically introducing controlled amounts of copper particles, the research team has created not just one new material, but an entire family of them, each with thermal, mechanical, and dielectric properties that can be tailored for specific, demanding applications. These advancements are more than just incremental improvements. They represent a significant step towards the future of electronics, a future where our devices are not rigid and fragile, but flexible, resilient, and seamlessly integrated into our world. From wearable sensors that monitor our health to the foundational technologies that will power next-generation communication networks, the potential impact is vast. This work provides a powerful blueprint for the materials by design paradigm, lighting the path toward a future where technology is smarter, more capable, and more adaptable than ever before. This groundbreaking work was led by Dr. Emad Mousa, with vital contributions from Rania Salama, Mohammad Abu-Abdeen, and Professor Gamal M. Nasser. Their collaborative research pushes the boundaries of material science and opens up exciting new avenues for future innovation.
As we come to the conclusion of this episode, I would like to take a moment to express my deep gratitude. I am Professor Dr. Salah Lotfy, professor at the Egyptian Atomic Energy Authority, and on behalf of myself and For Science Salah Lotfy channel, I would like to extend sincere appreciation to the researchers for their outstanding effort in producing this remarkable study. The research team includes Associate Professor Dr. Emad Mousa, Physics Department, Faculty of Science, Cairo University, Cairo, Egypt; Miss Rania Salama, Research Assistant, Volume and Fluid Flow Department, National Institute of Standards, Giza, Egypt; Professor Dr. Mohammad Abu-Abdeen, Physics Department, Faculty of Science, Cairo University, Cairo, Egypt; Professor Dr. Gamal M. Nasser, Physics Department, Faculty of Science, Cairo University, Cairo, Egypt. Their work represents an important contribution to the advancement of materials science and its future applications in technology. I also want to sincerely thank all of you, our valued viewers, for following For Science Salah Lotfy channel. Your interest and support encourage us to continue presenting the latest in scientific research. We invite you to share your thoughts about this study in the comment section below the video. Your opinions, insights, and questions are always welcome and add real value to our scientific dialogue. Thank you once again for watching, and stay tuned for more scientific explorations here on the For Science Salah Lotfy channel.